Hello, welcome to another module of this course, Microwave Integrated Circuits. We are now in week 8, and in the past few weeks we have been covering the various aspects of amplifier design, especially active circuits design like gain, then the frequency response, then noise, matching, and other things like that. So here we will take yet another concept that is frequently associated with linear circuits or amplifiers and mixers, which is the linearity, the measure of linearity. So in this module, the first thing, what is linearity? What do you mean by linearity? So if you consider a memoryless system, now in a memoryless system, the output and input relationships can be written like this. So if my input xt is like this, of this form, a in cos omega t, then the yt that I get will be like something like this, where yt follows this relationship that I have given earlier. So a in plus just if I can continue here. So this is this whole thing multiplied by cos omega t, and then below that we have so you see that if I just consider the fundamental component, then that fundamental component will have an amplitude alpha 1 a in plus 3 alpha 3 a in cube upon 4. So now, so the output at the fundamental frequency will have an amplitude given like this, and the gain at the fundamental frequency for a particular amplitude a in will be equal to now the thing with this alpha 3 is that it is usually negative. If it is usually negative, then you see with increasing a in, this value will become, this component will become more and more negative, and it will subtract from this alpha 1, and as a result what happens is this gain it will have follow a curve like this with increasing amplitude. The gain, if I use the red pen, So, you see this gain will follow a curve like this, and because that alpha 3 is negative, so as the input amplitude increases, the gain will gradually reduce from what it should have been by 1 dB at for a certain value of the input power, which is known as the 1 dB compression point. So, this is that value of the input power for which the value of the gain will be 1 dB lesser than what it should have been. And in fact, in terms of those alpha 1 and alpha 3, this 1 dB compression point is given by so at the 1 dB compression point we will have 20 log G A in 1 dB, that is this power. At this power level we will have the gain, which should have been, had it been a perfectly linear system, then this would have been the gain, but 1 dB less than this. So, this is one way of characterizing the linearity of a system. This 1 dB compression point is a very important figure of merit, and you will see various circuits are characterized by 1 dB compression point. However, the limitation of this 1 dB compression point is that this is a figure of merit at a particular frequency only. We are not considering the effect when we have, say, multiple frequencies present. In other words, if we have multiple frequencies present, will that also have an effect on gain reduction like we had for at a single frequency? Let us see that. So, suppose we have a system where we are introducing two frequencies, closely spaced frequencies. So, this is our amplifier, and say we have two frequencies at omega 1 and omega 2, and say this has some kind of, this is a nonlinear system, that input output relationship some nonlinear way. Now, let us see if we suppose our x or our xt, since now we have two tones or two frequencies at the input, we can write our input xt like this. So, then now this y1, y, if we use that same expression for y that we had used earlier, that is yt and xt are related by this relationship, this equation. So, then with now two tones present, the output yt will be given like okay, it will be something like this. Now, what you see here is now that we have two additional frequency components. One is at a frequency 2 omega 1 minus omega 2, and the other at 2 omega 2 minus omega 1. So, at the output what we will have is, we will continue having our original tones at omega 1 and omega 2 with an amplitude given like this and this, and two other components at omega 1 minus omega 2 and omega 2 minus omega 1 with amplitudes given by these values. Okay. Sorry, let me A1 square A2. This will be A2. This is A1 A2 square. Okay, just this small correction. Okay, so the output will now look like this. So we will continue having our original frequencies at omega 1 and omega 2, and in addition we will also have omega 1 minus omega 2 and yet another frequencies at 2 omega 2 minus omega 1. So this is the problem here. Now what happens is that the problem with this setup is somewhat like this actually. Suppose originally we had our two tones, and then this is, suppose these are two interferers at omega 1 and omega 2, and say if this is our desired channel, then say this is our desired channel of frequencies that we want to amplify. Now after passing through this amplifier, we will get outputs like this. But then now this interferer will now occupy our desired channel. So this is our desired channel. This is our desired channel, and then this is the problem, that this is a problem that is seen in the receiver, that we have a desired channel, but because of the interferers there are now additional components in the desired channel, and thereby it corrupts the desired channel. The other scenario could be, suppose especially at the transmitter side. The transmitter side, say we have two desired channels with center frequencies at omega 1 and omega 2 that we want to transmit. What happens at the output is that in addition to the desired channels, so the desired channels will now be amplified, we also have now interferers. So these are the interferers. In fact, so significant is this distortion produced by this effect, this intermodulation. This effect is known as intermodulation. Not harmonic modulation, intermodulation. That is interference between, caused by two different frequency tones. So significant is this distortion that there is actually just like that 1 dB compression point, there is actually a measurement quantity, a quantity used to characterize this distortion, and it is called the third order intermodulation product. Or IP3. We can solve that A out, that particular value of input for which, so IP3 is defined as that value of input power for which the fundamental amplitude of the fundamental signal is equal to the amplitude of the intermodulation products. So we have alpha 1 is equal to Okay, and this in turn, as you know, the amplitude of the intermodulation product is equal to so from here we get this A in IP3 So, this is the slope of the intermodulation products, which is 3:1, whereas the slope of the fundamental is 1:1. And the point where the two meet is called the input power at that particular point is called IIP3. It is the A in IIP, it is the IP3. So, this is the definition of the intermodulation product. So, here you have A out in dB, this is A in along the x axis in dB, and this is the slope that the third order intermodulation product follows, and this is the slope that the fundamental tone follows. Now, this deviation from this straight line is due to the compression, gain compression. However, if we ignore the gain compression, then they would have met at this point, at a certain point, and that point is the IP3 value. Okay. In fact, there is a relationship between the IP3 and the output intercept point and the output 1 dB compression point, and that is nearly equal to the input third order intercept point and the input 1 dB compression point, and that is equal to 3/4/145, and that is nearly equal to 10 dB. Okay. So, what you have is that this say if this is my IP3 point and say this is my 1 dB compression point, then there will be a 10 dB difference between the two on the output axis. If you want to find out the output of a cascaded, when suppose we have a number of stages cascaded. So, we have our stages like this. So, these are the nonlinear coefficients of the nonlinear polynomial. So, you have this y2 is equal to beta 1 times y1 plus beta 2 times y1 cube, beta 3 times, sorry. Now, this y1, and if I further write the relationship between y1 and x, then the relationship comes out like this. and then the total input the total IP3, if suppose A in is the total IP3, and this will be lesser or equal to 3 by 4 alpha 3 beta 1 plus alpha 1 cube beta 3 upon alpha 1 beta 1, and this relationship can simply be written as, so I have 3 upon 4 alpha 3 beta 1 plus alpha 1 cube beta 3 upon alpha 1 beta 1. This is equal to 1 over the input intercept point of the first stage like this. So, from here we can say that 1 over the input intercept point total is equal to 1 over input intercept point of the first stage multiplied by the gain of the first stage over PIP3 of the second stage. So, from here we see that the input, the IP3, the linearity of the end stage in the chain of cascaded stages matters the most. So, this is opposite to the effect of the noise figure. In the case of noise figure, we saw that the noise figure of the first stage in the chain matters the most. In the case of IP3, the linearity of the last stage matters the most. So far, we have been analyzing some of the parameters used to characterize the linearity of a circuit. But let us now see some of the methods in which how we can improve the linearity. So one of the ways, if we go to the slides on the monitor, is a method called power combining. Now, power combining, since as you see that the linearity will decrease with increase in input power. So, if we could separate, if we could have individual amplifiers which will individually amplify the signal, and then at the output we combine the various powers, then that would improve the linearity of the circuit. So, this is one method where you have an input matching network and then 3 individual transistors, each of which produce their own amplification, and then finally at the output of the transistors the powers are combined through an output matching network. But the problem with this particular circuit is that if any of the transistors fail, then the whole system fails. And also these resistances, the output resistances have to be fine tuned so that there is proper balance between the individual circuits. So yet another way of achieving this power combining is using a power divider, or repeatedly using power dividers. We repeatedly divide the powers and then combine, then amplify the individual signals, and again they combine it using combiners. One other way, what happens during combining is that the overall linearity of the transistor or the IP3 of the transistor is not improved, but just that the curve is shifted a bit. So, if initially this blue curve was representing the transistor's input output characteristics, now due to this power combining, the entire characteristics shift rightwards, and so we get the the input power at which the saturation or gain reduction starts happening is now shifted to a higher value, and that's why we are getting that higher value of gain. Then yet another method of achieving this linearity is what is known as feed forward linearization. So here since the output of this amplifier can be thought of as the combination of the correctly amplified input signal plus some error. Then if we now have a system where we can use this error, where we can remove this error. So to do that, what we do is this output signal is now subtracted from its own version using a delay, so as to account for this delay of this amplifier. Then it is if that the linearly amplified part is subtracted, then all we will have remaining is the error part. And if that is also while combining in this summer, if we pass it through an attenuator having an attenuation equal to the amplification of this amplifier, then what we ultimately get here is the error signal divided by the amplification factor A. Now if we again pass this through an identical amplifier, assuming which has very little noise or which produces very little non-linearity, because the input signal is at a very low level, so it is much further away from its non-linear region. So what we get at the output is the epsilon, that is the error factor again, and now if we again subtract it from this signal after proper delays, then we can get back the correctly amplified version of the input with no non-linearities present. Ideally no non-linearity should be present, but in practice some non-linearity is always present. The problem with this is the correct tuning of the devices, that is we need two identical stages, then these delays have to be tuned, this amplifier has to be tuned, and also we need two summers which have to be accurately working. Also, since we need two amplifiers for this function, it is also an inefficient. It improves the linearity, but it reduces the efficiency. So, so with this, we come to an end to this module. In this module, we have discussed about the various parameters used to characterize the linearity of a circuit and some of the techniques used to improve the linearity. Thank you.